So I'll take your question at the end. So at between you do not speak, okay, but then I'll record it. So this is the second tutorial for this session in calculation of capacitance and the reactance. So tutorial 1 we have covered, which was much like calculating the problem in inductance. Let us see what is the tutorial second. Here you have conductors 3-phase. So when we say A, B, and C, these are the 3 phases of the conductor. Now, what type of conductor is this? Here you have a bundle conductor. Bundle conductor means that a single phase conductor can have more than one conductor. So here we have 2 conductor bundle because 2 conductors are there for a single phase. So it is a 2 conductor bundle. You have to calculate the inductive reactance per kilometer. Now, what is inductive reactance? When we say that inductance of the line L, so if there is an inductor which is having the unit of millihenry or Henry, then if I need to convert that in ohms, that is the impedance of this inductor, then in that case, I will be going with inductive reactance, which is directly related to the frequency of the system. So it is called XL is equal to omega into L, where omega is basically 2 pi f and L is in the unit of Henry or millihenry. So here the unit of frequency is in hertz and the unit of omega is in radian per second. So if the frequency is given in radian per second, you can use this formula. If the frequency unit isn't given in hertz, you can use this formula to determine the inductive reactance per kilometer. Now, why the per kilometer? Because the distance throughout the parameters are distributed. So here we need to calculate the parameters per kilometer of the line or the per length of the line. Now the distance D is given to be 45 centimeter. 45 centimeter is the distance between 2 individual bundle conductor of the line. You need to calculate the GMR, that is the geometric mean radius, at 8 centimeter. Now here you have between the phase A and phase B, there is a distance of 8 centimeter. Between the phase B and C, there is a distance of 8 centimeter. And between the phase A and C, the distance is 16 meters. Sorry, the unit is in all meters. So I believe that here it will be in meters. Find the per unit series reactance of the line if its length is 160 kilometer. Now here you need to calculate per unit system. Now what is per unit system? If I need to calculate the per unit value of a quantity, it is basically the actual value of that quantity divided by the base value of the quantity. So suppose for a power system network, so many devices are connected. It can be a transformer, transmission line, generators. Then the base value of that system is constant throughout the power system network. And the individual devices, whether it is a transformer, transmission line, or generator, its actual value is divided with the base value of the entire power system to get the reactance or the impedance, we can say, in per unit. Now the total length of the line is 160 kilometer and the base has to be taken at 100 MVA 345 kV. Now you understand here the unit is given 100 MVA. What is the MVA? MVA stands for megavolt ampere. So basically if we talk about the power, we have a complex power S which is divided into real power P and the imaginary power Q. This is a reactive power. So S is equal to P plus JQ, where P is the real power, its unit is in watt. Q is the reactive power, its unit is in volt ampere reactive. And then the complex power unit is in volt ampere. That is the product of voltage and current. Mega is a bigger unit, 10 to the power 6. So we have 100 MVA the power. 345 kV is the line voltage of the system and the base has to be taken on that system. Now understand the difference between a single phase and a 3-phase system first. When you have a single phase system, all the voltages will be given between line and the neutral. Whereas when the voltage for a 3-phase system, the voltage will be given between line to line. So the 345 kV, it is not mentioned whether it is a line voltage or a neutral voltage. You have to understand that 345 kV is basically the line to line voltage of the system, and the base value has to be taken on 100 MVA 345 kV base. So we will solve these two parts of the question for the geometrical consideration given in the problem. So here we have been given the GMR of the conductor. So the GMR, that is the geometric mean radius of the conductor, is basically given to be 8 centimeters. So here there is some confusion in the unit. It should be in centimeter or meter, anything, because unit should not be a confusion. So here it can be centimeter. So the GMR means geometric mean radius, which is the distance between two individual phases. So you have the phase A and the phase B. So the distance between two phases A and B, or the line A and B, we can say that the GMR is 8 centimeter, which is converted to meter, that is 0.08 meter. Now the GMD of the line, the GMD is basically the equivalent distances when compared between A, B and C phases. So you have three phases, A, B and C, that you have to take. So the distance between A and B is 8 centimeter. The distance between B and C is 8 centimeter, and the distance between A and C is 16 centimeters. So the cube root, that is the number of conductors which are involved, number of conductors. So you have three conductors involved, so three phases, multiplied by the distance L1, L2 and L3. You will be getting the GMD. So GMD comes to be 10.08. Now you need to calculate the inductance of the line, which is with the formula 2 into 10 to the power minus 7 ln of GMD by GMR. So the GMD by GMR, you take the natural logarithm, you will get multiplied with 2 to the power minus 7, you will get the inductance of the line. Now, coming to the inductance, we get 9.672 into 10 to the power minus 4. What is the unit? The unit is in Henry per kilometer. So per kilometer of the transmission line, we are determining the inductance. Now, if we multiply this with the total length of the line, then we will get what is the total inductance of the entire transmission line. We were asked to determine the inductive reactance, XL. So XL is basically 2 pi f into L or omega into L. So here the frequency is 50 hertz. So many times in the problem, the frequency will not be given to you. In that case, you have to take the frequency of your respective country. Whether you are in India, then frequency is 50 hertz. In US, the frequency is in 60 hertz, which is constant throughout the country. Now the length, the inductance of the line per kilometer, we are multiplying it. Then we are getting 0.3038 ohm per kilometer. Now here we are getting the unit is in Henry per kilometer. Now here we are getting ohm per kilometer. So in the problem, sometimes we will be asked to calculate the inductance. Sometimes the problem will ask to calculate the inductive reactance. Then we have to perform one more step to find the inductive reactance of the line. Now coming to the per unit system, we were given the base value. These are the base value. So base value is 100 MVA with 345 kV. Now the base impedance of the line. So we know that impedance is basically equal to voltage square by the power we take, that is the complex power S. So here kV base square divided by MVA base will be the impedance of the base impedance of the entire power system. So this formula is important. You have to remember this formula. The base impedance ZB is equal to kV base square divided by MVA base. Now understand, at the numerator you have the voltage and the unit is in kilo. So here always you will be taking in kilovolt, and the denominator is in complex power, but the unit is in mega. So here you will be taking in the form of 10 to the power 6. Otherwise, you will be committing a mistake in determining the base impedance. So the base impedance of the line we are getting 1190 ohms whereas the total length of the transmission line is 160 kilometer. So we are getting the base impedance of the line, and the total length given to us is 160 kilometer. Now, the inductive reactance of the line that we have calculated in ohm per kilometer, now we have to multiply that with the total length of the transmission line, that is 160. We will be getting the inductive reactance as 48.48 unit is in ohms. Now here we are getting the unit is in ohms, not in ohms per kilometer, because we have multiplied that with the total length of the transmission line. Now coming to the per unit system, we know that actual value by base value. So we have the actual value of the system, of the component, the base value of the actual network. ZB we have already calculated as 1190 ohms, and the inductive reactance for the entire power system of 160 kilometer length transmission line, we are getting 48.48. So X per unit of the line is coming to be 0.040. Now understand here that the numerator is having a unit of ohms, the denominator is also having the unit of ohms. So ohms and ohms will cancel out, and the per unit system will be unitless. So it is dimensionless quantity which you have to determine. That is, the X per unit is coming 0.04. Next problem, find the capacitive reactance. Now you have to determine the capacitive reactance. So it means we have to determine the value of Xc. The susceptance per kilometer, susceptance means we have to calculate the B. And that is the reciprocal of the capacitance of the line of a single phase line operating at 50 Hz. Now understand here the phase is given to be single phase. It is not a three-phase system. It is a single phase system. So whenever you have a single phase system, all the voltages will be in between the line and neutral. The voltage will be line and neutral, and that is known as the phase voltage. So the difference between a single phase and three-phase system will be in terms of the line voltage and line current. So there the term phase will be used for single phase, and for three phase you will be using the term line quantities. The spacing between the center is 6 meter. So for a single phase, the spacing between the center of the conductors are 6 meter, and the diameter of the conductor is 1.608 centimeter. So this is the diameter of the conductor. You have to determine the capacitive reactance and the susceptance per kilometer of the single phase transmission line. Now given the diameter of each conductor, you have to convert into SI unit, that is in meter first, to have all the calculation in the same unit. So diameter converted to meter, we need to calculate the radius of the conductor. So we have to divide the diameter with 2. So this is the basic fundamental we get to determine the radius of the conductor. Now remember, one very important point here is that when we are solving the problem based on inductance, then we are taking the fictitious radius of the conductor. But when we are solving the capacitance problem, we are taking the actual radius of the conductor. Fictitious radius we have taken 0.7788 into the actual radius. Now this is the difference between the inductance and capacitance initial calculation. So these mistakes should not be. The capacitance formula with respect to neutral. Now here we have a single phase system. So with respect to neutral, we have to calculate. So it is 2 pi epsilon 0 ln of d by r. Again, d by r stands for the GMD by GMR. The unit is in farad per meter because we are calculating all the units per kilometer of the transmission line. Now epsilon 0 is basically the permittivity of the vacuum, which is equal to 8.854 10 to the power minus 12. Unit is in farad per meter. Now these epsilon 0 value will sometime be given in the problem, sometime will not be given in the problem. So you have to memorize this value of epsilon 0. Now the GMD we need to calculate. The GMR is already given to us for a single phase transmission line. Now let us put the GMD and GMR first. Since the system is single phase and the GMD is given to be 6 meter, that is the distance between the conductors. So we have to put the formula of GMD here, that is 6, and the GMR is basically the actual radius of the conductor. We are not taking the fictitious radius as we have taken in the inductance. Now all the values we have to substitute in the capacitance, and then with respect to neutral, we will be getting the unit is in farad per meter, and this is the solution that is in farad per kilometer. So the bigger unit is in kilometer, we have to obtain. So meter has to be converted into kilometer. Then here the unit is in farad per kilometer. We have to obtain the capacitive reactance. So Xc is equal to 1 by omega C, where omega is equal to 1 by 2 pi f into C. So here we will getting the value of Xc. Now understand this Xc unit is in ohms per kilometer, right? Here we have a farad per kilometer. So here you will be having ohms per kilometer. So after substituting this value of the capacitance and the frequency, you will be getting the capacitive reactance of the line. So Xc value you will be getting as this one, which is in ohms per kilometer. Now the susceptance is basically the reciprocal of the capacitive reactance of the line, 1 by Xc. So the susceptance we are getting in the unit of mho per kilometer. So this one we are saying to be mho or rather Siemens. So we can say this one as Siemens also. We are getting 2.64 into 10 to the power minus 6 mho per kilometer as the susceptance of the line. Problem third, find the capacitance, that is C, the capacitive reactance, that is Xc, for a 1 kilometer of a single circuit 3-phase line. Now this is important. We have to note that this is a 3-phase line operating at 50 Hertz as shown in the figure. So we have the phases A, B and C we can take. Now these also depends because sometimes you have a phase like RYB, sometimes you have a phase sequence like RBY, but this is an equilateral triangle, so we do not have any confusion like what phases I need to take. If the length of the line is 280 kilometers and the normal operating voltage is 220 kV. Now here, whatever the voltage is given, 220 kV, understand this is a 3-phase line. So the voltage is basically the line voltage given, line voltage of the system, that is 220 kV. You know that there is a relationship between line voltage and phase voltage as the line voltage is equal to √3 times the phase voltage. So if the line voltage is given, you have to take that only, not the phase voltage. In single phase, you will be having phase voltage. Find the capacitive reactance to the neutral. So Cn value you have to determine capacitive reactance for the entire length of the line. Charging current also you have to determine. You have to determine what is the value of the charging current per kilometer and the total charging current in megavolt ampere. Diameter of each conductor is 2.772 centimeter. So we have been given the diameter of the conductor. We have been given the distance. Now here the distance is given 11.4. So obviously this is not an equilateral triangle, which I said you previously. So this is not equilateral because the distance is 11.4 meter. You have to determine the capacitance, capacitive reactance, charging current you have to determine. So these are quantities you have to determine. Let us see the solution. So here the diameter is 2.772 centimeter. You have to first obtain the radius of the conductor in meter you have to obtain because meter is the SI unit. So you have to convert that in meter and obtain the radius as diameter by 2. Given the frequency of 50 Hertz. So we have given the frequency of 50 Hertz. Now we can obtain the value of the capacitive reactance of the line Cn, which is the formula, the same formula what we are using to pi epsilon naught ln of d by r. So that formula we have to use and obtain the value of capacitive reactance Cn. The capacitive reactance per kilometer we have, because here we have the meter, so we convert that in kilometer because the total length of the line is given in kilometer. So capacitive reactance Xc, here the unit is in farad, so I have to convert that in ohms per kilometer first. So that will be 2 pi Fc. Capacitance unit is in ohms per kilometer. Now you will be getting the total capacitance in ohms per kilometer. then the total length of the transmission line is already given, that you can multiply. Now, what is the reactive power which is absorbed? Reactive power is √3 times the line voltage into the charging current of the system. So you know that whenever there will be a capacitance, so some current will be involved, which is known as the charging current. So since it is related with the reactance, so this reactance is giving the power in reactive power. So Q, if you have the resistance R, so that will give the power in the real power P. So now here, since the capacitance is involved, XC, we will be getting the power as the reactive power. Okay, reactive power is the imaginary power. So reactive power is equal to √3 times the line voltage multiplied with the capacitive reactance or capacitive charging current. Okay, now if we substitute the line voltage as 220 volt, which is given to us, and the charging current, whatever is there, that we have to substitute. We have to determine the charging current. So you know that there is a relationship between the current, admittance, and voltage. So I is equal to Y by Y into V. This is the relationship between current, admittance, and voltage. So admittance Y is the reciprocal of the impedance of the line. So when we are dealing with the impedance, we are basically dealing with the value of XC. So Y is the inverse of impedance. So we are getting the value of XC, 1 by XC. Now, if we put that here, I is equal to V by XC, we will be getting the charging current of the line. So this is the charging current of the line. So here, on substituting that values, we will be getting 37.6 megavolt ampere reactive. Now this unit is in var, megavolt in reactive. Fourth problem, calculate the capacitance to neutral per kilometer. Capacitance to neutral you have to calculate per kilometer of the single phase line. Now this line is in single phase of two single strand conductors having diameter 0.656 centimeter. This is the diameter, spaced 300 centimeter apart, 750 centimeter from the ground. So we have been given the distance of the conductor with respect to ground also. So you have the ground here, this is your ground, and this is your transmission line L. You have a 750 centimeter above the ground. So this is 750 centimeter. And the conductors are spaced at 300 centimeter apart. So if you take the line to neutral, it is 300 centimeter. Considering the presence of ground effect, neglecting the ground effect, two different cases are there. You have to compare the results of the capacitance calculation. So line spacing is given 300 centimeter. You will be getting, convert that into meter. So meter will be 3 meter. Diameter of the conductor is given 0.656. You obtain the radius of the conductor in meter. So here the spacing is in meter. The radius is also in meter. That is the fundamental unit. Neglect, first case, you neglect the presence of earth. There is no earth. That is the case 1. The capacitance with respect to neutral formula is 2 pi epsilon ln of d by r. The unit is in farad per meter. The unit will be in farad per meter. So if you substitute the values of the GMD and the GMR, you will be getting the value of the capacitive reactance, the capacitance in farad per meter. Okay. So after that, if you consider the second case, that is the effect of earth. First, we have not taken the effect of earth. Now we'll be taking the effect of earth. So the capacitance with respect to earth formula is 2 pi epsilon naught ln of d by r. Now one extra term is there, which is 1 plus under root d square by 4h square. Where h is the distance above the ground. So this is your ground, and here the conductor is there. So h is the distance above the ground. Now d is 3 meter, radius is 0.328 10 to the power minus 2 meter, and the distance of the conductor above the ground is 7.5 meter. So you can determine the capacitance with respect to earth, and that is calculated with respect to neutral point, not the between the conductors. So the capacitance with respect to neutral you will be getting 8.178 10 to the power minus 12 farad per meter. So what is the conclusion? The capacitance to neutral is more when the earth effect is considered. So considering the effect of earth, your capacitance will be more. Now understand, if you have a line and the ground, you will be having the capacitance between the line and the ground, which is equal to Cn. That is the capacitance between the line and the ground. Suppose you have one more conductor here. This is line number 1. This is line number 2. Then this capacitance is known as the line to line capacitance. So there is a difference between neutral capacitance, that is line to neutral, or the ground. Then this capacitance is known as line to line. Now, what is the difference between a neutral and a ground? That also you understand. So if you have a three-phase system, star connected network, so here you have line number 1, line number 2, and line number 3. All three lines are there which will carry the current, and the common point is known as the neutral. So this neutral can be grounded. So here you have it. Okay, this neutral and ground can be connected solidly ground, or it can be have a resistive grounding also. It can have inductive grounding also. So depending upon the system, what type of grounding is preferable, that type of grounding is used. The fifth problem, you have a three-phase system now here. So you have a three-phase system, double circuit. Double circuit means that here you have A, B, and C. That is the three-phase A, B, and C. Now the A dash, B dash, C dash is basically constituting the double circuit line. The diameter of each conductor is 2.0 centimeter. The line is transposed. Now, what is the meaning of transposed line? Transposed line means that if you have the three phases A, B, and C, then after a distance of L by 3, so if you have the total distance as L here, then after a distance of L by 3, the position of the conductor is changing. So we will be having the position of the conductor. This one is A, this one is B, and this one is C. After again L by 3 distance, you will be having the position to be changed. Now your A is there, so A will come here. Now C is here, so C will come here, and B will go. Why we are doing this transposition? So that over the length of the transmission line, the capacitance remain the same. The capacitance do not change. So that is the reason we are doing the transposition of the line. Now it carries a balanced load. What is the meaning of balanced load? Balanced load means that if you have a three-phase system, now here you have a three-phase system. Suppose one load is connected here, that is ZL. One load is connected here, that is ZL. And one load is connected here, that is ZL. Okay. So if you take this load, so all this load ZL is basically having the same magnitude, that is known as the balanced load. Because if the load is balanced, then only the current which is involved in individual phases will be equal. If this is ZL1, ZL2, and ZL3, then the load that is flowing in the individual phases will be different. Find the capacitance per phase to neutral of the line. So this is a double circuit line. 2 meter is the distance between the phase A and phase B. 2 meter is the distance between B and C, and total 4 meter is between A and C. So the diameter is given to be 2 centimeter. So here the diameter is given 2 centimeter. Convert that into meter first. Obtain the radius. This is the first point that you have to do. Now what you have to do is that you have to calculate the distance between the bundling of the conductors. So what is the distance between A and A dash? So between A and A dash, your distance is already given, that is 6 meter. This is already given. The distance between the phase A and its bundling B dash, okay, this distance you have to calculate. The distance between the other bundling, that is the distance between the B and C bundling, you have to calculate. Okay, this type of bundling. So all the distances you have to calculate between the each phase and its bundle of positioning. Once you have done that, you have to calculate the GMD, that is the mutual GMD of the line. Then these calculations you have to do it from the geometry. So once you have done this calculation, you can obtain the D equivalent. We have three phase MB is equal to 3. Then the product of that, DAB, DBC, and DCA, under root of that, you will be getting the GMD of the line, mutual GMD of the line. And these distances you have to calculate from the individual phase of the line. Now you have to obtain the GMR, geometric mean radius, for the individual phases A, B, and C, and then you have to obtain the GMR of the line. So again, you have the 3 here because you have 3 phase conductors, and all the individual GMR calculations that we have obtained for this, you have to substitute and obtain the GMR of the line. Once you have obtained the GMD and GMR, now the time is to determine the capacitance of the system with respect to neutral. So here you have the GMD calculation, here you have the GMR calculation. So what type of problem you have, the basic formula remain the same, that is 2 pi epsilon naught ln of GMD by GMR. Only difference is that whether you have a single phase conductor, 3 phase conductor, you have the double phase doubling conductors, you have to calculate this GMD and GMR properly to get your answer correct. So here the capacitance value we are getting with respect to neutral for the 3-phase double circuit line. Now the problem 6th, find the susceptance. So we have discussed the susceptance B is the inverse of the capacitive reactance of the line XC with respect to neutral per kilometer of a double circuit. Now the line is again the double circuit, so you will be having A dash, this is one double circuit, B dash, this is second phase, C and C dash, this is the third phase. There are 3-phase line with transposition as shown in the figure. Given the distance is 7 meter, so the distance between A and B is given to be 7 meter. The radius of each of the 6 conductor is 1.38 centimeter. So the radius is already given, that is 1.38 centimeter. So distance is given between the phases A and B. Other phases are also the same distance, B and C, and between A and C you have the distance 2. First, you have to obtain the radius in meter. So here the radius is given in centimeter, you obtain in meter. Then you have to obtain the GMD calculation first. So first you obtain the GMD calculation. GMD calculation means the distance between the phases A, B, B, C, C. So what is the value of the individual phases? The distance DAB. How many options are there that you have to calculate? Once you have obtained the GMD calculation, that is DAB, BC and DCA, you can obtain the other calculations of GMD and GMR. So the D equivalent, which is basically the GMD of the line, this is the GMD of the line. There are 3 phases, so 3 multiplied with the individual distances that we have obtained, DAB, DBC and DCA. Then we can obtain the GMR of the line. So GMR of the line we have to obtain individually, DSA, DSB, DSC, and then we can put the formula here in DS. So here you have the GMR calculation. Again, you have 3 phases and the individual distances. So here you are getting the GMD, here you are getting the GMR, both are in meters. So the capacitance, now we will be getting 2 pi epsilon naught ln of GMD by GMR, which is coming to be in farad per meter. So we can substitute the value of GMD here, we can substitute the value of GMR here, we'll get the capacitance with respect to the neutral point, and then you have to convert that in kilometers. So always you have to convert the capacitance in farad per kilometer. Okay. The susceptance B is basically 1 by XC that we have seen it. So XC you have to calculate as equal to 2 pi F into the capacitance with respect to the neutral. Then you can get what is the value of the susceptance of the line. So the susceptance of the line, the unit will be in mho per kilometer or Siemens per kilometer. So this is the susceptance of the line, you have to substitute, and then you can obtain all the calculations which are involved in the capacitance calculation of the line. So usually all the problems that belong to the capacitance of the line involves either the single phase or the 3 phase. You have to calculate the capacitance with respect to neutral, capacitance of the total length of the transmission line, the charging current, and the susceptance of the line, with the presence of earth and without the presence of earth. These are the possibilities by which you have to calculate the capacitance of the line.